solid state, we are going to talk about semiconductors now. As you have seen under the point effects, with the addition of impurities, we can change the properties of semiconductors by introducing extra electrons or creating holes in a pure silicon structure. In pure form, semiconductors having electron in the valence band, these are all the electrons, and it having a upper level known as a conduction band. When electron go from valence to conduction, in conduction band electrons will act as a conductor, or they transmit the electricity, but in the valence band they don't, they are in a bounded state. So the energy gap between the conduction band and valence band is known as band gap. Larger the band gap, poor the conductivity of a semiconductor. Now here we are going to see in N-type semiconductors, that is the semiconductors in which we have doped pentavalent impurities having 5 electrons. In those, the donor level, this is that N-type, the energy level has gone so high. Originally it was here, electrons has to jump from here to here, but now electrons has to jump from only from here to here. So the band gap has been reduced drastically by this donor energy level has gone up. Valence bond energy level has gone up. While in p-type impurity, what happens? Acceptor level energy, this conduction band will come down. So from valence to conduction band transmission is very easy in p-type of semiconductors. Remember that. This is acceptor level come down in p-type. In N-type donor level, this electron donation level has gone up. This is how the band gap is reduced in both p-type and N-type. Band gap energy is reduced basically. Semiconductors have revolutionized our lifestyle, or all the devices we use. Simplest among these are diodes, which is a simple combination of N-type and P-type semiconductors, and we use them as a rectifier. What happens here? We having N-type region having excess electrons, P-type region having excess holes. So when we put them together, certain holes and electrons will merge and giving us this p-n junction, depletion layer. So we connected the N-type to the forward basing. We connected the N to N-type and P to P-type. So what happens? Electrons are pushed through it, holes are pushed through it. So this depletion layer will reduce, and we are getting good conduction of electricity. So this is a basic about our p-n diode. There are also another sort of solid states like group 13 to 15 semiconductors. What we'll do, the mix of group 13 and 15 like antimony, indium, aluminium phosphorus, gallium arsenide. These semiconductors have revolutionized the modern day life because of their fast response. The design of semiconductors devices have improved like anything. Let's take certain examples. Infrared lighting, diodes, laser diodes, solar cells, optical windows, they all use these semiconductors we just mentioned here, like gallium arsenide having a huge application in diode manufacturing. This is laser diode. This is our solar cells. So semiconductors having a tremendous application, and still these new materials are under research in the form of superconductors or better diodes that can be used in various applications. Another semiconductors are possible in group 12 and group 16, which are zinc sulfide, cadmium sulfide, cadmium selenide, mercury telluride. There are certain examples of group 15 and 16 semiconductors. Concept is the same. Zinc supplies excess electrons, sulfur requires 2 electrons. Same thing goes to cadmium sulfide. Cadmium selenide is based on the same concept. Now, these are the electrical properties of semiconductors. Let's discuss. In metals, if we see, there is no difference between valence band and conduction band. In semiconductors, there is a little gap, like when this band gap is less than equal to 3.2 electron volt. Semiconductors. Insulators, this band gap is very huge, and from the conductivity point of view, metals having a conductivity of 10⁻⁷ per ohm per meter. They are good conductors like silver and gold, copper. Insulators like rubber, many asbestos, many other materials. Semiconductors like silicon, germanium. So basically the band gap energy defines whether a particular material will be metal, semiconductor or insulator. Now, another important properties of solid state compounds. Basically we are talking about magnetic properties. Now, magnetic property of an atom is arising out of electron movement that we know, and because of electrons only, all materials acquire their magnetic properties. Each electron of an atom behaves like a tiny magnet. So, how it's going to influence its magnetic properties? First, because of the spin of an electron is spinning around its own axis, and with the spin it generates magnetic field. Just like Earth, the rotation generates magnetic field. Second is magnetic field due to the orbital motion around nuclei. So both these factors will give us a magnetic moment from an individual atom. And by the combination of these two, we are getting a total effect. Now, how to measure the magnitude of magnetic field associated with an atom? Because it's very small. So correspondingly, same scale is used to measure the magnetic field of atoms. The basic unit of measuring the magnetic field of an atom is bohr magneton, represented by μb, and it is equal to 9.27 10⁻⁻24 ampere meter square. This is known as bohr magneton, basic unit of a magnetic field of an atom. Now, magnetic field we know comes out of because of the electron's rotation around the nucleus as well as its rotation around its own axis. And an atom may have many different electrons present in different orbitals. So how in particular metal, alloy or solid state material will behave. Correspondingly, we can classify into different categories. Like first is paramagnetic materials. Paramagnetism means they having unpaired electrons, and these materials are attracted slightly by magnetic field, and they getting magnetized in magnetic field. Like copper 2 positive, ferric, chromium 3 positive, they all are paramagnetic due to presence of unpaired electrons. Next is ferromagnetic substances. Ferromagnetic substances are very strongly attracted by the magnetic field, like iron, chromium oxide, cobalt metal. They are ferromagnetic materials. And in ferromagnetic materials, these individual atoms group together to make a domain. These small there be like a small magnetic regions. These domains, when put under a magnetic field, they totally align themselves with a magnetic field. The ferromagnetic materials retain their magnetic field once magnetic field is removed or switched off, unlike paramagnetic materials, which are magnetized only till magnetic field is on. They have aligned totally along the magnetic field and retain their magnetic capacity after the field is removed. This is due to the presence of small magnetic domains that first randomly oriented, but under applied electric magnetic field, they totally align themselves. Antiferromagnetic materials. Antiferromagnetism has a domain structure similar to the ferromagnetic substances, but the domains are oppositely oriented and cancel out each other magnetic moments, like manganese oxide, iron manganese compounds, nickel oxide. And you see here, they're cancelling each other out. So these are antiferromagnetic materials. We having a domain-like structures, but these domain-like structures are cancelling each other out. Ferrimagnetic materials. In ferrimagnetic materials also, they are like a ferromagnetic materials, but their domain structure or domains magnetic properties do not cancel each other out completely. They have parallel and anti-parallel directions in unequal numbers. Thus, magnetism in these are poor than ferromagnetic substances, because domains are not totally cancelling each other out. Diamagnetic materials. Diamagnetic substances are weakly repelled to the magnetic field, like water, sodium chloride, benzene. This is because they having only paired electrons, and they don't have any unpaired electron that leads to a certain directional magnetic field. So they are slightly repelled by the magnetic field. Crystal defects we are going to discuss in solid materials. We have talked